China has finished a magnet that weighs 582 tons. It's the largest ever built for a fusion reactor, and it has exactly one job: hold something 7 times hotter than the center of the sun, without ever touching it. That's not a figure of speech. The material does not get held by a wall or a container or anything solid at all, because there is no substance on Earth that survives contact with it. Steel will not melt. Steel would vaporize instantly and take the experiment with it. So the machine holds it with nothing. A magnetic field shaped like a donut keeps the hottest thing in the solar system floating in a vacuum a few feet from a metal wall it must never reach. And this is not a machine waiting for its moment. A few miles away in the same city, a reactor called Emptiest has already held that fire steady for 17 minutes at a stretch. And here is the part that makes this a story about stars rather than about engineering. That reactor has to run hotter than the sun. Not as hot, hotter. And the reason why tells you something about our own star that almost nobody knows. The core of the sun sits at about 27 million degrees Fahrenheit. That's the number in the textbooks, and it is the engine of every warm day you have ever had. The Chinese reactor runs above 180 million degrees Fahrenheit, 7 times the sun's core, in a building in the city of Hefei. That sounds like it should be impossible, or at least unnecessary. If a star can fuse hydrogen at 15 million, why does a machine on Earth need 7 times more? Because the sun has 2 things we don't have, and both of them are enormous. The first is weight. The sun contains about 333,000 times the mass of the Earth, and every bit of it is pressing inward. That crushing pressure squeezes the core so hard that hydrogen nuclei are forced close together, whether they like it or not. We can't build that. There's no way to pile up a star's worth of mass in Hefei. It is worth pausing on how hard that squeeze is. The core of the sun is compressed to roughly 13 times the density of lead. Not 13 times heavier, 13 times denser, while still being a gas, held in that state purely by the weight of the star sitting on top of it. Nothing on Earth is under that kind of pressure, and nothing we build ever will be. The second is patience. The sun is in no hurry. Inside its core, a single proton can drift for billions of years before it finds a partner and fuses. The sun has been doing this for 4.5 billion years, and it's not yet halfway through. It can afford a reaction rate that would be useless to us. We have no mass and no time, so we pay for both in temperature. Heat the fuel far past what a star needs, and the particles move so violently that they collide often enough to matter on a human timescale. That's the trade. The sun uses gravity. We use heat, and the heat is the harder half because heat is the thing that destroys everything it touches. Now the problem. You have the hottest material in the solar system, and it's sitting inside a metal machine. Nothing solid can hold it, not because our engineering is bad, but because the concept doesn't apply. At those temperatures, matter is no longer gas or liquid or solid. It's plasma, which is simply what everything becomes when it gets hot enough to tear its own atoms apart. And plasma touching a wall does 2 things at once. It wrecks the wall, and the wall kills the reaction because contact drains the heat instantly. So the plasma is never allowed to touch anything. The machine is a hollow ring, and around that ring sit enormous electromagnets. They generate a magnetic field that wraps the plasma into a closed loop and holds it suspended in the middle of the chamber in a vacuum, floating. The design is called a tokamak, a Soviet word from the 1950s, and every serious fusion reactor on Earth is a version of it. It helps to think of it as a cage with no bars. The plasma is a charged fluid, and charged things cannot cross magnetic field lines easily. So the field becomes a wall that has no substance, cannot melt, and does not wear out. There is one more thing inside that chamber, and it is nothing. The ring is pumped down to a vacuum better than the space just above the atmosphere. That matters because a single stray puff of ordinary air would cool the plasma and end the run. The hottest place in the solar system sits inside one of the emptiest places human beings can manufacture. It also does not work perfectly. Plasma is unstable by nature. It wobbles, it bulges, it finds gaps. Most of the last 70 years of fusion research has been the same argument repeated in different machines. Keep it still, keep it hot, keep it away from the walls, and do it for longer than last time. If you want to know how long they have actually managed to hold it, and what happens on the day the cage fails, subscribe and turn on the bell. The numbers are stranger than the machine. Which brings us back to the magnet. 582 tons is roughly the weight of 4 blue whales in a single piece of superconducting coil, and it is the largest object of its kind ever built. It was made entirely in China, which matters more than it sounds, because for decades the hardest components in fusion came from a small number of Western suppliers. It's not for the reactor that holds the world record. It's for the next one, a machine called BEST, still under construction, and the target attached to it is the part that made people sit up. China is aiming to generate fusion power by 2030. For comparison, the international project in southern France, the one 35 nations have been building together since the 2000s, is not expected to switch on until 2034. The cage with no bars needs bars after all, in a sense. Not around the plasma, but around the magnetic field itself. Every one of those field lines has to be produced by something physical, and the something is a coil of superconducting wire so large it has to be assembled where it will be used. There is a reason this particular component made news rather than the reactor it belongs to. For decades, the most difficult parts of a fusion machine came from a handful of specialized Western manufacturers, and any country building a reactor had to queue up with everyone else. A magnet of this size, designed and produced start to finish inside one country, means that queue no longer applies. The bottleneck moved. Here's the number that fusion people actually care about, and it's not a temperature. In January 2025, the Chinese reactor known as East held its plasma steady for 1,066 seconds. That is 17 minutes and 46 seconds. The previous record set by the same machine 2 years earlier was 403 seconds, more than doubled in 2 years. 17 minutes sounds unimpressive next to a power station that runs for months, but the useful comparison is the other direction. For most of fusion history, the answer was measured in fractions of a second. Getting to 17 minutes means the machine survived its own operation, that the walls held, that the field stayed stable, and that nothing drifted far enough to end the run. And in January 2026, the same reactor did something else. It pushed the plasma past a density limit that physicists had treated as close to unbreakable, and the result was published in a peer-reviewed journal rather than announced in a press release. Denser plasma means more collisions, and more collisions is the whole point. One more thing about that 17-minute run is worth translating out of the jargon. The plasma was held in what physicists call high confinement mode, and the plain meaning is simply this: the heat stays in. A plasma that is merely hot but leaks its energy everywhere is useless. A plasma that holds onto its own heat is the only kind that ever can power anything. That distinction is the difference between an expensive light show and a reactor. None of this is power generation. No fusion machine anywhere has yet produced more energy than it consumed and delivered it to a grid. What these records measure is control. For 70 years, fusion was a joke with a fixed punchline. It is 30 years away, and it always will be. That joke is now out of date, and the evidence is not scientific, it's financial. On the 30th of July this year, an American company called Commonwealth Fusion Systems raised another $1 billion, bringing its total to $4 billion. Its reactor is expected to produce more energy than it consumes in 2027. Its first commercial plant is planned for Virginia, and Google has already signed to buy half of that plant's output before the plant exists. That last detail is the one to hold on to. A technology becomes real not when it works in a laboratory, but when somebody signs a contract for electricity it has not produced yet. What changed is demand. The enormous data centers behind the current wave of artificial intelligence need more power than anyone planned for, and they need it constantly, day and night, in a way that solar and wind on their own cannot supply. That has turned fusion from a scientific ambition into a commercial race with buyers waiting at the end of it. So, there are now two strategies running side by side. China is building enormous state machines on a public timetable. The West is largely betting on private companies with venture capital and shorter deadlines. Nobody knows which approach gets there first, and both of them might. It's fair to ask why anyone is spending $4 billion and building 400-ton magnets for a machine that has never delivered a watt. The fuel is the first answer. One of the two ingredients, deuterium, is simply a heavier form of hydrogen, and it is already in the ocean. Every glass of seawater has some. There's no cartel, no pipeline, no country that owns it, and the supply outlasts any timescale a civilization needs to plan for. The second answer is what does not come out. Fusion produces no carbon dioxide at all. It produces no long-lived radioactive waste of the kind that has to be stored for tens of thousands of years, because it's not splitting heavy atoms. And it can't melt down for the reason we are about to come to. The third answer is that it never stops. Sunlight arrives when the sky's clear. Wind arrives when the air moves. A fusion plant, if it works, produces the same output at 3 in the morning in February as it does at noon in July, which is exactly the property that the electricity grid is short of, and that no amount of solar panels supplies on its own. That's the prize. It's genuinely enormous, and it is also the reason to be careful, because a prize that large makes everyone involved, including journalists, want the timeline to be shorter than it is. Somewhere in the last 10 minutes, you probably had the thought, we built a thing hotter than a star inside a city, and we are holding it back with magnets. What happens when the cage fails? The honest answer is disappointing, and it is worth saying clearly. Almost nothing happens. If the magnetic field collapses, the plasma touches the wall, and the instant it does, it cools. The reaction stops. It can't run away because it's not a chain reaction. Fission works by splitting atoms that release particles that split more atoms, which is why a fission reactor has to be actively held back. Fusion is the opposite. It has to be actively held up. Take away the machine and it dies in milliseconds. There's almost nothing in there to spill. The amount of fuel inside the chamber at any moment is measured in grams. There's no core to melt because there is no core. So that's the wrong worry. Here are the three real ones. The first is fuel. These reactors run on two forms of hydrogen. One of them is deuterium. It's abundant and sits in ordinary seawater. The other, tritium, is radioactive, decays quickly and barely sits on Earth. There is no tritium mine. A working fusion plant has to manufacture its own tritium while running, and no machine has yet demonstrated that it can make more than it burns. The second is the walls. Fusion throws off high-energy neutrons, and neutrons are not charged, which means the magnetic cage does not stop them. They pass straight through and hammer the structure of the reactor itself, degrading it over years and making parts of it radioactive. It's a far smaller waste problem than fission, but it's not zero, and it is an engineering problem nobody has fully solved at scale. The third is timing. Fusion is being sold as an answer to an energy problem that is urgent now, and the most optimistic, honest timeline puts meaningful fusion electricity in the 2030s or 2040s. It may well arrive. It may simply arrive after the decisions that mattered were already made. Nobody has run a commercial fusion power plant. That sentence is still true, and it will stay true for years. What has changed is that the question stopped being whether the physics works. It does. Stars have been proving it for 13 billion years, and the machines on Earth have now held the reaction for 17 minutes at a stretch. The question now is whether it can be made to pay, and how soon, and by whom. That's a very different kind of problem, and it is the kind that tends to get solved once enough money is looking at it. So the next few years are worth watching. 2027 for the American attempt at net energy gain, 2030 for the Chinese target, 2034 for the international machine in France. 3 dates, 3 strategies, 1 physical process that our own star has been running effortlessly in the sky the entire time. It's a strange thing to sit with, The sun does all of this for free with no magnets, no superconductors, and no funding rounds. It just has enough mass to squeeze hydrogen until it gives in and enough time to wait. We have neither, so we compensate with 180 million degrees and a 582-ton magnet and a cage made of nothing at all. And there is one machine on Earth built on exactly this principle. A ring buried underground where magnets hold something that must never touch the walls. It is the largest machine human beings have ever constructed, and unlike the one in Hefei, it has just been powered down. Two rings, the same trick, opposite directions. One is being kept alive, the other has gone quiet. And the reason it went quiet is a harder story than this one. Start there.